Okay, so after this introduction, so we in this lecture we will examine, so starting from the classical least square approach, then we move to the forgetting factor and the recursive least square with forgetting factor, and then the problem of the identification condition problem, and I just remark a few computational problems when you are developing your methodologies. Of course, now everything is optimized in your, especially if you are using the MATLAB, the MathWorks solutions. But of course, you can decide to perhaps due to the, I don't know, to the implementation of your solutions, perhaps they need to be specifically implemented in a very specific hardware, I don't know. So perhaps you need to develop by your own, so you need to implement by your coding method, by some coding approaches, your solutions, your software. So perhaps you need to know something about the computational aspects. So for this course outline, so we after in the previous lecture we saw some introduction and an overview on system identification. Then the previous lecture we mentioned, we examined in a little bit more detail the non-recursive or offline identification method, especially the least square and the prediction error method. Of course, we mentioned also the instrumental variable method, which represents a modification of the classical least square, is simpler than the prediction error method, but it doesn't provide a modeling of the stochastic part of the process. And then today we will consider the recursive identification method, and we start with the simplest one, recursive, and then we will examine the second one, which is the recursively square with forgetting factor. And then we will end the lecture with some practical aspects and application, and we will see in the next lectures, maybe the next week, an application for control. So as we introduced in this lecture, why we could need recursive identification. So the first motivation, as I already mentioned, was the need of an online estimation. I said that perhaps due to a change in the working condition of the process or the effect of a fault, the parameters are changing. The parameters of the process of your model are changing. So you need an online estimation because you need to continuously monitor your data and then to perhaps take some decisions. So it's why you can need you might need an online estimation. The second is that perhaps you are, as in this case, as for the case of this course, you are you intend to develop an adaptive system or an intelligent system. So with the need of adaptation, with this need of adaptation, of course, you need to continuously adapt with respect to the changing of your system. So again, you need something that continuously estimates your the parameters of your model. So again, as the third point, the time parameters. Why time variance? Because again, due to the effect of a fault, which as we already mentioned, the aging of an electric motor due to, for example, the overheating. So the parameters of the motor, for example, the DC motor is an exemplary example, are changing. For example, the value of the resistor, of the resistance, or of the capacitors, of the equivalent capacitors of the inductance. So they are changing. So you need to track some varying conditions. Again, in the context of fault detection and diagnosis, so you need to understand if there is something wrong in your process. So something that continuously, again, needs to check the conditions of your model. Or of course, you need to simulate the system. So something that.
Sorry, interrupt. You can ask a question about the third option.
Yeah. Yes.
Because you were talking about the parameters.
Yeah.
My question is about do this parameter have a negative or positive effect on our system directly or indirectly?
Well, no. Well, it depends on the case. In some cases, it depends on the effect. We don't know. Normally, I don't know. Some parameters can be modified in order, I don't know, to slow down your process. So. Okay. For example, I had some experience on an electric valve of an engine, and for example, due to the aging of this valve, the electric motor, which was controlling the moving of your valve, was due to the overheating or to the wearing out of your process. So this motor was moving slower with respect to the nominal conditions. Okay. So, for example, in this case,
from your viewpoint, some parameter have any effect on our system? Indirectly too?
Yeah.
Okay.
Yeah, can be. It depends. You should perform what we call a failure.
Depends on the scenario.
It depends on the fault scenario and also on the modeling of the faults.
Okay. Thank you so
much. Of course, it requires some extra information.
Yes, you're right.
But thank you for your question.
You're welcome.
So there are two options. As far as we know at this point, how we can estimate time varying parameters. Of course, at the moment, if you introduce any change in our solutions that we already examined, the first idea could be to continuously update the model once every sampling instant. So it means that you continuously apply your least square approach. So it means that if you remember, the idea could be, okay, of course, if you don't know an alternative approach, it means that you can estimate your parameters every time instant by continuously applying at each time step your least square solution, which was this one, if you remember, which was the basic.
You mean that the model must be updated in real time, yes?
Yeah. Okay. So if you just know this solution, which was the least square, the classical least square, it means that for at each time instant, you need to implement this equation with the new data, But of course, you remember the most time-consuming part of this approach was the inversion. Of course, you can think of some alternative approaches for solving this inversion. But in any case, the adaptation, the update of the model every time instant can be computationally expensive. So you must forget this idea. So it's impossible that at each time instant you implement the classical least square approach. So the solution, in fact, is to make use of the previous calculations in an efficient manner. So in fact, the recursive least square is based on the procedure which modifies the offline method. So it means that we are modifying the classical with what we called the block batch least square method in order to obtain a more efficient algorithm. Of course, you can also modify the prediction error method, but normally, as far as I saw, also in some applications we had with some project with the industry, they implemented the recursive least square. The recursive least square is enough when you want to integrate, for example, in an adaptive implementation of a controller. So it's something that the prediction error method is something quite complicated, if you remember, because the prediction error method is based on a minimization, a numerical minimization of a cost function. So it can be quite time consuming if you need to implement it. So normally for recursive least square, for recursive implementation or online implementation, you use the recursive least square approach. So normally, when you need to modify a recursive, or you need to implement a recursive algorithm, there are some properties that you need to consider and you need to think of about when you want to implement it. The first requirement is the fast convergence. Of course, if you think that something is implemented in a recursive way, it means that you need to reach your steady state condition very quickly. So the requirement of fast convergence is normal, is something also intuitive. The second point concerns consistent estimate. If you remember, the consistency means that your estimation, we didn't enter into the details of the consistency of the estimate, but a consistent estimate means that your estimate needs to converge to the, let's say, true value when the time tends to infinity. So this is the consistent. So means that the expected value of the estimation, of course, has to be arbitrarily near to the real value. If we know it, we don't, of course, in theory, I just put these quotes, means normally you don't know, it doesn't exist, this real value. But if it exists, the estimates needs to go quickly to the real value. The third requirement should be good tracking. So it means that when something changes in your process, your estimation, your time varying estimates need to be very quick and to go to the value, near to the value of your system. So it means it's something linked to the second point. So your estimates should be good, and then to quickly tracked by your system, your variables. The fourth requirement is, of course, is something that again should be is quite intuitive because it should be computationally simple. So it means that all calculations, if you think, should be performed during your sampling interval. So if your sampling interval is t, capital T, it means that all your computations need to be concluded within this time sampling interval. So of course, you can easily understand that this requirement can be quite important. In some cases, can be also impossible to meet, because if your sampling interval is very short, so perhaps you can be unable to perform all your calculations. So in this time interval. So it means that your algorithm should be as simple as possible. Of course, we will see that there are some trade-offs, some compromises, because, for example, convergence. The convergence requirement is in contrast with the tracking. So it means that we will see later in a couple of examples, that if you require fast convergence, it means that the tracking of your variables or your parameters is not very accurate. So it means that the speed of your estimation is in contrast with the accuracy of the tracking. We will see later that the more your convergence is fast, the more your estimate is inaccurate. So it's something that it means that you need to decide a trade-off between the speed of the convergence and the accuracy, the accuracy of your tracking. Another aspect is, for example, is the computational complexity versus with respect to accuracy. Again, normally you need to have a very accurate estimate. But an accurate estimate normally can be derived, for example, think of the prediction error method. Its accuracy is better than normal classical least square, but of course, prediction error method is much more complex than least square. So again, you need to decide a trade-off between the accuracy you need with respect to the complexity of your solution. In every application, there is a compromise, a trade-off. Of course, another point here, which is not included, but is the cost of your solution. We are assuming that we have a lot of money, so we don't care about the cost of the implementation in terms of money. But another important performance index that should be taken into account is the cost. How many dollars your solution cost? So the cost of your implementation in terms of money. It can depend on the hardware that you are using or the time that is needed to design your solution. It's something that is very important because, for example, if a company requires a solution that takes 1 year of work, perhaps the company cannot accept that you take one year for developing your project. So perhaps normally 1 month is enough. So again, cost means in terms of money or the time needed to develop your project. So again, another trade-off. We are not considering the cost of the solution in terms of money, but it's something that especially for your application, if it's a low-cost application, perhaps you should save money. So you need to, for a low-cost application, you need to use an hardware, especially a microcontroller, which is very cheap. Cheap means perhaps that the speed, so again, the frequency of the processor is very high. So the sampling time cannot be very small. Again, you need to consider this aspect. So let's see, just to recall the classical least square. So you remember that the solution given by the classical least square reads as the solution is given by minimizing this cost function, and as you remember, the cost function was computed as the summation of all the error, the square. So it's why we call least square, because it's a sum of all the squares. And if you remember, the tracking or the prediction error was computed as a difference between as we mentioned earlier, the reality and the model. And so we obtained the solution, which was the computation of the parameters vector, which was the inverse of the regressor matrix, and this vector multiplied by this vector. Of course, if you think of, as I already mentioned, if you think of a recursive, so recursive means that at every time instant you are acquiring data. So it's why the solution now here includes the subscript t, because the cost function is modifying during the time, because as you see here, t is increasing. At every time instant you are introducing new data. So it's why also the solution now depends on t, because all the matrices depend on the t. But again, it means that you need to compute this equation, as we already mentioned. This equation needs to be performed for at each time sampling time, which can be expensive due to the computation of this matrix. So from this consideration, I just remark this point here. So the criterion function changes every time step. Then the estimate changes every time step. So how we can derive a recursive implementation of this estimation without computing at each time instant this relation? So we, of course, without any demonstration of this approach, but can be easily derived because it's something that is using concepts based on linear algebra. So it's something it's very easy to obtain because it's based on the partition of this matrix into two matrices which contains the inverse and the another matrix which is added to this one. So everything can be demonstrated as using linear algebra. So it's something very easy to show. So at the end, in order to obtain this equation that is implemented online as a recursive relation, so we are using this algorithm. So of course, as a recursive algorithm, we need some initial conditions. So at the instant t 0, so at the beginning, at the instant 0 of your algorithm, you choose the initial values of your estimate. So normally, if you don't know anything about your estimate, normally the initial value of the estimate is equal to 0, because normally you don't know anything about this, the initial condition, the initial estimate. At least I don't know, if in some cases you know some rough value of your parameters, because perhaps you know that the model is derived by physical law, so perhaps you can include as an initial value as a preliminary value, which can be near to the real values. If you know it, you can include your known value. But if you don't know anything, please leave it to 0. And P0 is a matrix which, if you remember, is it represents the error of your estimation. Because if you remember, it's a covariance matrix it was the expected value. P was the expected value of theta of the estimation minus the real value transpose multiplied by the estimated minus the real value. So this was the covariance matrix of your estimation. So in fact, it represents the error with respect to the real value. So it gives you a measure of the accuracy of your estimation. So here we have the recursive algorithm, and as you can see here, the algorithm is obtained as an adaptation. So there is an adaptive law, as in every recursive algorithm, there is an adaptation law, which reads as follows. So the new value of the parameter, so this can be a vector, is obtained from the previous value of the parameters. As you can see here, we have the previous value of the parameters. So notice here that we have t minus 1 and t. So if t small t is it represents the sampling interval. So t is equal to the integer k multiplied by the sampling time. We have that the new value is equal to the previous value plus, so it's important here, you modify your solution, your previous solution, because if you remember, the parameter is changing, so the new value is the previous value plus there is a parameter k, which is varying with respect to the error. So this is clear that you can see very easily that if E is 0, epsilon, is 0, it means that your model at the current time is equal to the real value of the output. So it means that if E is 0, this equation says that you don't need to change anything, of course, because if the model is actually at this time is equal to the real value of the output, of course, you don't need to do anything. But of course, if this epsilon, normally this epsilon is different from 0, so you need to adapt your parameters according to this adaptive law. So the second equation says that if there is a change, if there is a modification, of course, change a parameter. If not, please do not do anything. The change is weighted by this parameter k. I don't know if some of you is familiar with neural networks. Normally, k in neural networks, in the training of a neural network, k is the learning rate, is something that is adapted according to the learning of a neural network. In this case, the k is something that depends on two factors, as you can see here. I just want to just to explain to you how it does work. I don't want to enter into the details of this adaptation because it's quite complicated, but in the correction here, the correction factors takes into account of two effects here measured by P and phi. So this K is, I can say that is proportional. It can be demonstrated, and just to clean here something. So it can be demonstrated that this, the adaptation, let's say the gain of your adaptation is depends, let's say in this way, depends on it can be demonstrated on the signal to noise ratio. So it means that if the noise is very high, as you can see here, so S is the power of the signal, of the input signal, N is the power of the noise. If the noise is very high, this k, the key of the vector, the value of k is it is reduced because it means that if your data, if your information that you are using for updating your parameters are not very accurate, if you think of it, it's better not to do anything. So it's why key, if n is very high, is very, let's say, I can, so as a general consideration, so we said that key depends on the signal to noise ratio. So it means that when n is high, it's quite intuitive, because if n, the noise is high, please k tends to 0. So it means not to not to update, please do not update your parameters if the information you are using is not very accurate. So it's something which is reliable, can be, if you think of it, is something that is motivated. And also the same occurs when the noise is high. If the noise is high, for the same, when the noise is high, also P tends to 0. So in this way, K is 0. So it means that please don't do anything if so. In general, I don't want to enter into the details to show these issues, but this is the point. So we have this modification, this adaptive law for the matrix P. So the matrix P is adapted in order to have this behavior of this adaptation. So in order to reduce the adaptation when the noise is very high, or the accuracy when the accuracy or the inaccuracy of your parameters, of your information is high. So please do not limit your changes, because you are relying on something that is not very accurate. So it's something, if the information is not true, so please do not rely on this information. So this idea is weighted by this adaptation, although this parameter can be complicated, but it works. We will see some examples. It works in this way. And again, also the fact that the information can be inaccurate or not very reliable is implemented in this equation. So it takes into account the fact that, as you can see here, I don't want to enter into the details, but you can see here that the vector phi contains the inputs, the effect of the input. So in some sense is including the effect of the power of the input here. And a final observation, because if you can notice that perhaps you have here you are dividing. So you can say, you can remark, oh, please check, because you are dividing. So you are hiding. You can think of like an inversion. But if you notice that this product is a scalar, so we have here a vector multiplied by a square matrix P and another vector. So this is a number. So again, there is no inversion. So you eliminated the need with this algorithm. You remove the need of an inversion of a matrix. So the inversion of a matrix was recasted into an adaptation algorithm. This is very important, because it is computationally simpler than the inversion of the matrix. So this is an important point. So how we can handle, because we mentioned also the problem of the time varying parameters. So normally there are two ways for managing time varying parameters. The first one, for those of you who are familiar with a first approach, so a first approach can use a Kalman filter. So Kalman filter is an alternative approach when you want to estimate parameters, especially time varying parameters. Of course, you know that the Kalman filter can be used for, I don't know if some of you are familiar with sensor fusion. So when you want to integrate more information or you want to filter out some noise from the data, a Kalman filter can be used in this way. Normally, if you are using a Kalman filter for estimating time varying parameters, so you need to include in your model the fact that the parameter is changing. So normally you have according to the method 1, you can include, for example, the changing of your parameters. So theta t plus 1 is equal to the previous value of the parameters, theta, plus theta at the time t, plus I don't know, a noise. And then you have the output of your system, which depends, of course, is a function of your input u plus a noise v. And from this system you design a Kalman filter. This is a first possible approach for estimating time varying parameters. This is not our case, because for our case we are considering, so it's why we are introducing the recursive least square. So the solution from our side is to use the recursive least square, but we make this assumption, as we mentioned at the beginning, if you remember. The parameters are changing due, for example, to the fact that the process is changing. If you remember why a process can change, due to, for example, a variation in its working condition, can be one motivation, and the second one, as we mentioned, due to a fault. So for one of these two effects, let's say causes, we need to forget the older data, because as we mentioned at the beginning of this lecture, if the model is changing, the past data are no longer valid. So if you think of like here a time scale t, you have, for example, the past. So we are considering the data. Here we have the data. Want to show you as a graphical way. So you have your data. The data are, of course, you know, u and y. Past and present. You can assume, for example, I'm changing the color here. There is a change. There is a change in your time series. And so it means that the past data you need to forget. So So you need to forget the past data because they are, due to the change, are no longer representative to the current situation, to the most recent. So I hope this is clear, this point. So you need to, in case of change, something is changing, as we will see later in a simulation, or perhaps the next week. I don't know if today. The data are changing. Data when, of course, the data means the sequences are changing, U and Y. So you need to forget the past data and to rely the most on the present, the most recent data. It's written here. So you need to modify the cost function so you can gradually forget the old data, and the model needs to fit to the most recent data. And in this way, the parameters are adapted to describe the newest data. Of course, it's impossible that in your model you remove. It cannot be done. So you cannot think of immediately removing the past data because it's unfeasible, it's impossible. So you must introduce something that gradually, as is written here, makes you to forget the past. So what is no longer valid? This is the basic idea. To me, is very interesting. It represents the key point. So forget the past and rely on the present situation because is the only one which represents the current, the real situation, because if something is changed, is no longer valid. So the idea was solved in a mathematical way by modifying the cost function. The cost function, because is also a basic way. So because that the solution here is derived by minimizing the cost function. So you are introducing a weighting of your cost function because that the least square is weighting without any weighting of the cost function. The classical least square, where the weighting is one, is considering at the same with the same weight, with the same importance, all the data. Because if you remember, the solution is obtained by minimizing the summation of the equation error, the square of the tracking error. When you need to forget the past data, it means that in your time scale, I can do like here. I don't know, in order to clarify, I don't know if is normally beta, the function beta with the time works like this, has this shape. And I include also a description. So here we have the past. And here we have the present. So it's clear that when the data are closer to the present, which is the idea of the recursive least square with forgetting factor, the weighting of your cost function is closer to 1 because the algorithm needs to rely the most on the most recent data. And if you see here, if you follow here, I can put like a division, a partition between present and the past. The past, as you can see here, the beta function goes asymptotically to 0. So it means that as long as the time increases, in the past, your function beta goes to 0. So it means that these data are multiplied by a number which goes to 0. So it means that they are no longer affecting your cost function, which is, if you think of it, is really the need is the point, is the effect we need to have in this solution. So to forget the past data, so the idea of the forgetting is obtained by, again, by multiplying the data of the into the cost in the cost function by a parameter which slowly goes to 0. So this is the idea of forgetting, how we can forget the data, by multiplying them by a parameter which asymptotically goes to 0. And how we can rely on the most recent one? By multiplying the most recent data by a factor which is 1. And when the data becomes, the present data becomes past, they are in a recursive way modified and included in a cost function. So in a mathematical representation, the dynamics of this cost function is obtained by considering this is a difference equation. When beta is multiplied by a factor lambda, this is again an adaptive law. As you can see here, the previous value of beta is multiplied by a parameter lambda, which gives you the value of beta at the instant t. The final value of the data of beta is equal to 1. This is a particular difference equation where the condition is given at the final value rather than at the initial value. And this is a difference equation which has, for those of you who are familiar with, is the same of a differential equation, but it is in the discrete time. So it can be shown that this difference equation has a solution which is given by this function lambda up to t minus k. Lambda is what we call the forgetting factor. It's very important, this forgetting factor, because it's a factor which has a range between 0 and 1. As you can see here, when lambda is equal to 1 from this equation, you have the same of the recursive least square. So it's something that is very important. So the recursive least square with forgetting factor, when the forgetting factor is 1, you have the standard, you obtain again the standard least square. So with no forgetting factor, of course, because beta is 1, it means that beta is not entering into the cost function. So you obtain the same solution of the classical, let's say, recursive least square. And let's see how the solution is modified. How the solution is modified. So it's modified in this way, with an algorithm which is called weighted least square. We will see in the, I can include some code in order to show you this algorithm. So the algorithm of the weighted is called weighted recursive least square. Has the same form of the classical, let's say, recursive least square, because if you notice here, we have the adaptation law, the equation error, here epsilon, so is the tracking error, and then we have the computation of the gain here, k. But you can see here that the only difference between the weighted least square and the normal recursive least square is that in the computation of the matrix P, the lambda appears as the denominator 1 divided by lambda, and here this equation lambda multiplied by, so divided by lambda plus this term here. So the most important, however, if you notice here, the most important effect is clear here at the beginning, because you know that lambda assumes value between 0, of course it cannot be equal to 0, and 1. And if you notice, as soon as lambda goes to near to 0, it means that also P goes to 0 and also K becomes high. Is high. So in fact, the effect of lambda can be very important, but also can be very dangerous. Because if you think that when lambda is 0, you can see here 1 divided a value of a number which is very small. So 1 divided something that is very small becomes very high. So P is very high. And so if P is very high, you have K, which is very high. So from one side, if, just to point out this issue, if P is very high, you notice here K is very high, so adaptation here, fast, you have the effect of fast adaptation. Of fast adaptation, which is I put here a positive aspect, or we can, in a fancy manner, we can, like a smiling face. On the other side, K, which is high, means that the algorithm is sensitive to noise. And again, sensitivity to noise means that we will see that we have, so once in one side, fast adaptation, which is a positive behavior of an adaptive algorithm, because if you remember, you need fast tracking. We can put here also fast tracking. But on the other side is a negative aspect. So we have a face which is not smiling because we have a poor, let's say, poor accuracy of your estimation, because you are amplifying. It can be shown that if you consider it as especially if you think of it as a filter, which filter, so if you transform it as a transfer function between the input and the output, which is the estimate of your parameter, you can see that it amplifies the effect of the noise, which is very which can be very dangerous. So when you are selecting the value of your lambda, as it will be remarked later, you need to select it quite near to 1, because you want to reduce the effect of the noise, so you want to obtain a good accuracy of your estimates. But on the other side, you need to select quite close to 0, because you want to a fast tracking, fast adaptation. So there is, depending on the noise of the data, there could be an optimal value of lambda that can be estimated. So it's why at the beginning, as you remember, we mentioned the effect of the Kalman filter, because if you remember, the Kalman filter is designing the gain of your filter in order to minimize the effect of the noise. So also in this way, there is an equivalent representation of the Kalman filter as a recursive least square algorithm. Of course, the problem, I forgot to mention that when you design, for those of you who are familiar with the Kalman filter, is that the Kalman filter can be designed if you know the matrices, or the covariance matrices of the noise processes affecting your model. So it is another problem. While the approach of the weighted recursive least square doesn't need to know the statistics of the noise affecting the data. You can play with the lambda, In order to show you the effect of just we will see later, perhaps we have some time the next week to show some examples, but I can show you here if you need, if you notice, there are two values of the lambda. So a lambda closer from 0, you can see here that so lambda is 0.9, and there is here this is a model where two parameters are changing. So you have I don't know if you can read it, we have the value of the parameter which is changing. The change is happens according to as a step, with a step function. So we have a parameter here. We have two parameters which are changing. They are called A and B. So the first value is changing from, let's say, I don't know, 0.7, and in the middle of the simulation, the parameter is changing at the value, I don't know, 0.2 or 0.3. And as you can see here, the tracking is quite fast, because in blue you have the estimation, and the estimation, so the parameter is tracked in a very fast, quick way. Also for the case of the parameter B, from 0.5 goes to 0.1, and as you can notice here, there is almost no delay. So the tracking is very fast, but as you notice here, the accuracy of the estimation is very poor, because the estimation is changing very quickly. So it means the accuracy is not very high. But if you notice here, especially for the case of the value B, lambda tends to 1, so is the value 0.97. You can see here that the tracking is lower, so there is a delay. You notice that the parameters there is a transient, is not so as quick as here, but takes, I don't know, I can say, I don't know, takes 205, let's say 300, perhaps 300 data, 300 samples before reaching the steady state here. But the estimation is smoother than the case where lambda is 0.9. So the accuracy is better. And another, just to before the break, we can see here that we have the solution in red, which is provided by the classical least square. So if you are not considering any recursive, so it means that the classical least square takes all the data as a batch, and it finds this value. You can see here that the estimation, the solution provided by the classical least square is something in the middle between the two values of the parameter, which is wrong, because you cannot use the traditional least square, because there is a change. So the new value of the parameter here is different from the past value. So the only way that has the classical least square for managing this behavior is to make like an average. So in fact, the least square are averages the solution. So it's something which is in the middle, but the solution provided by the least square is not equal neither to the past value or the new value. Is totally wrong. But I put here just to show you that the solution provide, in case of changing of time varying parameters, the solution provided by the classical least square, where there is no adaptation, is totally unreliable, so is wrong. And I continued here just to show you that with lambda 0.8, the solution is even slower, but is also more accurate, because you can see here that is very smooth. And as a final value, lambda is equal to 1, you can see here that in the first a first set of data before the change, so there is no change. The classical least square finds the real value of the parameter, but of course, when there is a change, so because the data, also the past data, are included in the least square, it gives you at the end the value of the classical least square, so which is wrong. So if in case of parameter change, if you use the least square estimate, it's wrong. It's not reliable. It gives you a wrong answer because you are including in your cost function also the past data, which are no longer representative of the real condition of your process. And you include the new data, but of course, you are also considering the past data, which are no longer valid. So it's why the classical least square fails when there is a change in the parameters. I included also some code which I will take into account the next lecture. So we can, if you are interested in implementing or examining the solution, or perhaps in your studies, you need to implement a least square approach. So you can refer to this code. It's very simple, and we will comment it later in the next lecture. So I think it's better now. We can stop here 15 minutes and then to conclude this part by examining some details on some numerical implementations and some details on this algorithm. So if you agree, we can stop here and have a 15 minutes break before restarting again.